So now that we have studied applications of phase rule in a one component system, a very simple system consisting just water, we are now going to apply our understanding to more complex system, and we are going to start with two component systems. The two component systems. And these systems, two component systems, when you mix more than one chemical constituents, they are going to behave slightly differently from, let's say, a pure one component system. And this behavior can be classified into three main types. The first one that you're going to see are the solid solutions. Solid solutions. And then after that, we'll study eutectic systems. And finally, we are going to go to peritectic, the peritectic systems. Uh, so before we start, so what we're going to start with the first one, which is your solid solution systems. What exactly is a solid solution? As the terms imply, solid solution is nothing but a mixture of two solids, and in which you cannot differentiate one solid from another. It is easier to intuitively imagine this, that if in case of, let's say, if you have liquids, because you make solutions of liquids in your daily life, what you do is the most simplest thing that you do when you're making tea or coffee, you add sugar to water. Now if you take them separately, sugar is a different phase, water is a different phase, but when you mix them together, it is very it is impossible to separate one phase from another. Remember, when we were studying the definition of what a phase is, so a phase is a constituent of a system which can be physically or mechanically separable from rest of the system. So here, because I cannot see where sugar is, so if I cannot point out where exactly sugar is within this system, so sugar is not forming a separate phase, rather it is has the similar phase, or it has the same phase as the rest of the system, and both sugar and water form a single phase system, and that is your water sugar solution, the water sugar solution. Now another example, everyone uses stainless steel in their homes. So stainless steel is made up of iron and nickel. So these two are different metals which are forming your stainless steel. But if someone asks you to, if you have, let's say, a glass of steel, and someone asks you to pick out where is nickel, where is iron, you will not be able to do it, because iron and nickel, they are mixing together and they are forming a single phase. So these sort of systems in which two chemical components combine together to form a single phase, we call them as solid solution. So now what is the basic solid solution that we are going to study in this lecture? So in Igneous Petrology, the most studied solid solution is your plagioclase system. The plagioclase system. Now, if you remember from your mineralogy class, plagioclase is a series within your Feldspar mineral group. Your Feldspar mineral group has three end members. You have albite, which is your sodium-rich feldspar. You have anorthite, which is a calcium-rich feldspar, and you have orthoclase, which is a potassium-rich feldspar. Now the series from albite to anorthite, this is your plagioclase series, the plagioclase series. Similarly, you have another series which goes from albite to orthoclase, and that is known as your alkali feldspar series. Now, if you look at these zones, so whenever you have this albite and anorthite or orthoclase within this compositional range, which is defined by this line, so there they are going to form the solid solution. And the rest of the region, for example, this one, if this is your bulk composition, your feldspar, they are not going to form solid solution. So within this lecture, we are going to focus on this plagioclase series, which is made up of two end members, albite and anorthite. Now, what is the formula for albite? So, albite is given by formula NaAlSi3O8, and anorthite is CaAl2Si2O8. And these form solid solution where there is exchange of Na plus 1 Si plus 4 with Ca2 plus and Al3 plus. So if you look at these, so this is total plus 5 here, and you have total plus 5 charge on this side also. So as a unit, NaSi is being replaced by CaAl if you go from albite to anorthite. Now what we are going to do is we are going to understand their behavior in a phase diagram. So what you have here on your screen is a phase diagram of albite and anorthite system. And I want to mention that all phase diagrams are experimentally determined. It is not a law of nature or something like that. So people have actually melted real feldspars or real plagioclase to determine this solid solution. Now I want you to take a good look at this picture. So what we have here is, on the x-axis you have your composition, and on the y-axis you have your temperature in degrees Celsius. And on the x-axis the composition is plotted in terms of weight percent of your anorthite component. So if you are on anorthite end, you have 100% of anorthite component, whereas if you are on albite side, you have 0% of anorthite component. And if you're in middle, you have both, some part of it is albite, some part is anorthite. So you will not write a formula NaAlSi3O8 or CaAl2Si2O8. Here some of your NaSi is replaced by Ca and Al when you go from albite to anorthite. Now within this phase diagram, we can identify three main regions. The first region over here, the second one, and the third one. So within this first region, what you have? You have a liquid phase. So anything that is above this temperature curve, above this curve on temperature and compositional diagram, is going to be in liquid phase. Then in the second region, which is between this curve on the upper side and this another curve which is on the lower side, you have a plagioclase plus liquid phase. So you have two phases. So you have a solid and a liquid. Now you come to this bottom curve here, and below this you have again only a single phase, which is your plagioclase. Another thing that I want to mention within this curve is that this curve, you have these two variables, composition and temperature, and this phase diagram is drawn at some pressure which is fixed. So at a fixed pressure, if you change your pressure, this curve will change. If your pressure changes slight, it will change slightly. If you change pressure by a lot, so this curve will also change by a lot. So what we have here, we defined three regions here. The first one in which you see liquid, then the second region where is liquid plus solid, and the third region which is only solid. So this curve on top here, this one. So this curve on top, this one. This defines the boundary between liquid and the solid plus liquid region, and this curve is known as the liquidus curve. Similarly, the curve at the bottom, which separates plagioclase plus liquid from plagioclase phase, is known as the solidus. And remember, throughout these zones here, so you have plagioclase, and you also have plagioclase in this zone. It coexists with a liquid. In both these zones, plagioclase forms a single phase. So you don't have a separate albite mineral or a separate anorthite mineral. You have a single mineral which is called plagioclase. It may be rich in compositions in that like it can have high calcium content or low calcium content, but it is still going to form a single phase.